I'm going to use this. Thank you very much for the introduction. Thank you very much to the organizer for asking me to give this talk. I'm very honored, and I'm very pleased to be here in Toulouse. This is my first time, although the tight schedule of this conference makes it quite difficult to visit the town. But I'm sure that we will enjoy a nice dinner this evening and perhaps a stroll in the center. Okay, so the topic of this talk is time integration of differential equations. And yes, and in particular, geometric numerical integration and structure preserving algorithms. So I want to give a short introduction explaining what this topic is, what I mean by geometric numerical integration and structure preserving algorithms. But then I will focus on some topics that are more dear to my heart because I've been working on this for a long time. And in particular, I'm talking about Lie group time integrators. And I will consider a basic introduction of these methods. I'm not going to assume any previous knowledge about them. I will describe some connection to control systems and consider some error analysis in the context of Riemannian manifolds. And then I will discuss a little bit energy preserving and methods on Riemannian manifolds. And I will try to pepper this with some applications. In particular, I will show you something about applying these methods for discrete gradients, discretization of gradient flows for INSAR and for diffusion tensor imaging, and perhaps some applications in shape analysis on Lie groups. Okay, let's get started. Here is my introductory slide on geometric numerical integration. So classical methods, the classical approach to solve differential equations, especially ordinary differential equation, has been such that you want to design methods that solve a large class of problems. And this is perhaps true, this is certainly true for Runge-Kutta and multi-step methods, but it's perhaps true also for some classes of methods like finite elements and finite differences for PDEs, even though less so, we can say. So in the last 25 years, this sort of point of view has been changed, and people are starting looking into methods which are purpose-built. They want to look at methods that preserve geometric underlying structures of the ordinary or partial differential equations that you are trying to approximate. And in particular, here are some examples. So for example, for time integrators, symplecticity is one of the main things that you would like to preserve if you're solving Hamiltonian systems. Then you have reversibility, phase volume, preservation of first integrals, Lie group, and manifold structure. So I will focus on these two in my talk, but the others are definitely also very important. In PDEs, we have similar structures, but for example, for example, if you preserve topological structure in finite element methods, sometimes you get for free stability, existence and uniqueness of solutions of the discrete equations. Okay, so this is really strong property and desirable property. Other things that you would like to conserve are local conservation laws, local conservation of energy and momentum, and other local conservation laws for Hamiltonian PDEs. One of the main success stories in the context of geometric integration is backward error analysis of Hamiltonian systems. So what is backward error analysis? You're looking at, you have your problem, your ODE, and you have a numerical method that you apply to this problem. So you have a numerical flow and an exact flow that you want to compare to see what they do for you, if they have good, if the numerical solution is approximating well the exact solution and so on. And how do you do that? How do you compare them? Well, you're asking the following question. You want to find a vector field, fh, which is an approximation of the original vector field, and such that the solution or the flow of this vector field at discrete times coincides with the numerical solution. This is the idea of backward error analysis, okay? So find the modified vector field which solved exactly gives you at discrete times the numerical solution. So it turns out that this vector field can be expressed in terms of an expansion like this in powers of the step size. H here is the step size of your integrator. And in particular, one important tool in this analysis are B series. So you can express these write these expansions here indexed on rooted trees in an appropriate way, which I'm not going to describe in detail. But what is it? This is a particularly important tool for analyzing symplectic methods or for analyzing geometric integrators in general, because, for example, for symplectic methods, it turns out that this modified vector field is also an Hamiltonian vector field. And then you have a preservation of a modified energy, and this modified energy can be also expressed as an expansion of this type, okay? So, well, okay, that's nice, but even more important is that this is the first step for proving important properties of the method, like this implies, after some work, linear error growth and long-time preservation of energy for symplectic methods applied to completely integrable Hamiltonian systems, or to perturbed completely integrable Hamiltonian systems. So these are strong properties which are very desirable from a numerical method. However, this is a little bit difficult to generalize to PDEs. And the reason is that in order to get the analysis right, what you need to do is to truncate this series in an optimal way, because not always or quite often these series are divergent series. So you have to truncate them optimally, and this is not so easily done in the context of PDEs. It's tricky. It's much more trickier, we can say. So the challenges in the context of PDEs are a number of them. And in particular, backward error analysis doesn't work so nicely anymore. It's not so easy to generalize. So perhaps one has to think of more advanced tools to do this. Symplectic or Hamiltonian PDEs and symplectic discretizations should be generalized, and one proposal is these multisymplectic discretizations. But again, the existence and uniqueness of solutions of the discrete equations is not very well understood, so one should work on that. Especially convergence is not at all well understood, and there is a lot to do in this area. Another thing that is a challenge for the future is simultaneous preservation of several preserved quantities, several geometric properties. This is a challenge also in the case of ODEs, not only for PDEs. And then a number of other open problems are to be considered. Okay, so what I'm going to do now is to start my simple introduction to Lie group integrators. I would like to stress one thing. Since this is a conference in geometry science of information, I will focus mostly on applications which have something to do with data and optimization problems, rather than looking at mechanical systems and variational integrators, for example. And this is a choice that I've done because it's too much to cover both areas. But definitely, I think in the audience, there are people who are experts in variational integrators and would give a presentation of variational integrators much better than me. So let me start with these simple ideas about Lie group integrators. Suppose let's go back to the Euler method, just to, everybody knows what the Euler method is and they are familiar with it. So suppose we are integrating an ordinary differential equation and we apply our Euler method. The step size here is h as before. And what we do, we approximate the solution at time tn plus 1 by means of the solution at time tn by adding h times the vector field f evaluated at yn. Very simple. Okay, so how can we think about this? We can think that this, from yn, we solve exactly a very simple ordinary differential equation with a constant vector field. So here, f of yn is depicted here in this example of the Duffing oscillator. At this point, the vector field of the Duffing oscillator is coinciding with this constant vector field. And the Euler method is simply propagating the solution along this tangent, along this constant vector field for a short time h, okay? So can we sort of generalize this simple idea to something a little bit more advanced? This is what you can do with a Lie group integrator. So suppose that we write our vector field in this form here. So we can write it as a sum of two linear vector fields, very simple. But then we have this function here in front of the second vector field because our vector field is nonlinear. So, and we look at the commutator of these two vector fields and these two are not commuting, okay? So these three vector fields, they generate a Lie algebra. Okay, if you take commutators, you can see that this is the algebra, the Lie algebra SE2. What do you do with a very simple Lie group integrator? Instead of propagating your flow along the constant direction, along the tangent, you are propagating along a linear vector field. And the linear vector field is obtained as follows. You take the two vector fields up here, linear vector fields up here, and you evaluate this function here at the initial condition, or at the point x0 is equal to y0 is equal to 0.75 in this example, okay? But then you compute your flow, exact flow of this along this simplified linear vector field, okay? For a time step h, okay? And then it's clear from this picture that there is some potential here, right? You can get a much better trajectory if you allow for going along linear vector fields rather than constant vector fields. Huh? So how do you generalize this simple point of view to get to higher order? Let me describe a little bit of that and go back to some important references here. Here I have two seminal references in the context of Lie group integrators. The first one is a paper by Crouch and Grossman, which proposed to use frame vector fields to integrate for integration of manifolds. And the second one is another seminal work where it's a series of works, really. It's not just one paper by Lewis and Simo, where they study symplectic and energy-preserving integration of Hamiltonian systems on the Lie group SO3, okay? And also on SON, but for certain type of problems. There is another important, very important reference in this field, which is the famous paper by Moser and Veselov. And you can say that that paper is the seminal paper for the variational integrators in some sense. Although it contains a lot of other things also on completely integrable systems and how to discretize completely integrable systems. But that would be the third main reference if I had space on this slide. Let me describe just a little bit what Crouch and Grossman proposed. So suppose we have our ODE on a manifold. Suppose that we can write our vector field as in this fashion here, where F1 to Fd are a set of frame vector fields. So we assume that we can find a set of vector fields that span the tangent space to the point, at the point P, to the manifold for every tangent space, okay? That are able to span like this. Then, what you're doing, what I was doing in my previous example, if you like, is simply for designing an Euler method to propagate the flow, to propagate the numerical solution along the exact flow of a simpler vector field, a frozen vector field, which I obtain by this formula. So I keep the frame vector field as they are, but I freeze the functions which are possibly nonlinear, which are multiplying the frame vector fields, okay? Freeze them, evaluate them at the point P. And P, in my case, is going to be the solution at time Tn, okay? So how do I generalize this idea to higher order, to get higher order methods? Well, what one needs to do is to consider more complicated compositions of exponentials. So you're going to compute intermediate approximations of your ODE, which you call capital Y1, capital Ys, the so-called stages of your method. And then you're going to consider a composition of flows, like so, along frozen vector fields in these intermediate solutions, okay, intermediately defined solutions. These solutions here are found exactly in the same fashion, but just considering other parameters. The alphas here are simply parameters of my method, okay? So the thing is a little bit complicated. It's complicated in various ways because now the order analysis for these methods is not trivial at all. It's quite cumbersome, and also the fact the implementation is quite complicated, can be quite complicated, because it can be quite costly to compute all these exponentials. Okay, an alternative approach is the approach proposed by Hans Munthe-Koos, and he starts with a different setting, a different framework. So the idea is to consider a manifold where you have a Lie group action, a Lie group acting transitively on this manifold, and then what you're doing is we are going to use this Lie group action in order to express your solution on the manifold, essentially. But you have to do it together with the Lie group exponential. So you're composing the Lie group action with the Lie group exponential, which is a map from the Lie algebra to the Lie group. And then you are differentiating appropriately the composition of these two maps so that you get these infinitesimal generators of the Lie group action, and you get this map lambda star. Okay, so if you are composing the Lie group action dot here with the exponential, and you are differentiating appropriately, you get a nice map out, which is linear, and it's a map that sends any element in the Lie algebra to an appropriate vector field on the manifold. And with this, what you can in fact do is to create a set of frame vector fields. So by just taking any basis of the Lie algebra and transforming this basis by means of this linear map, you get a set of frame vector fields. So you can go back and do the methods of Crouch and Grossman if you like. But okay, let's see. So your vector field now in the point M can be expressed by means of these produced frame vector fields by means of the Lie group action. I said lambda lambda star here is linear, so I can pull it out here. I will have a format of my vector field of this type here, of this form here, where Fm here is a map that goes from the manifold to the Lie algebra. Okay, so that's what Munteco's, that's the setting that Munteco's described. And one way to look at his approach or his methods is simply as a change of variables. So now, as I said before, as I announced before, you use the Lie group action in order to represent the solution on the manifold. So you write YOT as an exponential of some curve in the Lie algebra, and the whole thing acting on the initial condition. And then the only thing you need to do is to find the differential equation that this curve solves, okay? And this looks like so, okay? So you make essentially a change of variables. Now this is an equation on a Lie algebra. It's a vector space. You can use any method you know for vector spaces in this context. So you can use your favorite Runge-Kutta method and propagate the solution in the Lie algebra and then map it back to the Lie group or to the manifold. In the case F is linear, I want to stress here for someone who is familiar with Magnus expansions, this expression here is very related to the Magnus expansion. In fact, you can recover the so-called Magnus expansion from here by just solving this equation by Picard iteration. Okay, so I gave you a little bit of ideas of how to, well, let me say a last remark, okay. What is the beauty of this change of variables? The beauty is that here the order conditions are extremely simple because you can use any Runge-Kutta method of your favorite order and you will immediately recover a solution on the Lie group which has the same order. So this is straightforward in this case. Okay, I've told you a little bit about the ideas, the simple ideas behind Lie group methods, and I told you about two ways of making these methods of higher order, okay, generalizing them to higher order. Now I'm going to discuss a little bit of connections to control, and next I would like to show you that this manifold formalism or format has in fact some applications, and I will single out one of them. Okay, So let's consider this simple control system. It's an affine control system. I have controls here, ui, for I from 1 to m, and vector fields at h high, which say are defined on some manifold, okay? So what is the interest? This is a very simple problem, a simple control problem. I don't have any drift vector field here. It's just to keep things simple. What is the problem one would like to address by looking at systems like this is how should I choose or determine the controls, assume that they can belong to a certain class of controls. And in particular, for example, I would like to address problems of controllability. It's one of the main problems of controls. Then I would like to know what is the ability of this system to bring the state, the y, to a final prescribed state in final time using the available controls. So controls belonging, for example, to a given space. All right, so in order to do this, I need to analyze this dynamical system. And I need to do it independently on the choice of the use, okay? Or assuming that the use are just functions belonging to this space. Okay, let us see a simple, very popular example, which is the example of control of a simple car. Huh? So in this case, the model, what you want to do is to park the car, parallel parking, which is so difficult for some of us. And so I believe that the system of ODE given here, with these two vector fields here, can in fact model this system, simple system of a car, and I would like to find the controls as simple as possible, so such that I can park my car. Then one important thing is that the commutator between these two, or the Lie bracket of vector fields of these two vector fields, is non-vanishing. It's a third vector field, and the three vector fields together give me a rank 3 matrix for any theta, for all theta. So this, in fact, expresses the fact that I can express all the solutions of these differential equations by using these three vector fields. And the system is controllable. So, as I said, controllability has to do with solving this differential equation or analyzing the solutions of these differential equations and figuring out how to choose the controls. And if we want to express, so if we want to analyze these solutions, we could think of expressing the solution of such a differential equation by means of a Chen-Flies series. And what is a Chen-Flies series? It's an expression of this sort for the differential equation, where we are going to consider our vector fields as derivation operators. And then turns out that you can, in fact, express every component. Say this phi says that you extract component number I of the solution by means of this form here. What are these alphas? These alphas are the coefficients of your solution or your expansion, and they are given as iterated commutators. Iterated integrals of the controls. And in order to keep track of the terms here, what you're doing is you are indexing over the set of words, and in particular we are having two vector fields here, so the alphabet for these words is just two indices. So turns out that this is a very important and useful tool for analyzing control systems. And another important tool that I will use, hopefully, in the second part of my talk is the collection of these iterated integrals. This is what's called the signature of a path. Suppose that the controls uj, they are coming from differentiating some function cj, okay, taking the derivative with respect to time. Then we call signature of the path c the collection of all these iterated integrals, okay? And what about them? Well, these iterated integrals completely determine the solutions of the control, the ODE. So these are important for this reason. So bear in mind this. I would like to draw eventually some connections to my Lie group integrators. And I want to make the following remark for this reason. Here, suppose that my vector fields in the previous problem are linear vector fields for the sake of simplicity. So they are given by a matrix A1 times Y and another matrix A2 times Y. Then I plug that in my controlled ODE, and I can rearrange the terms so that I get A1 U1, A2 U2. This is a matrix A of t times Y. So this is a time-dependent linear ODE, and A of t is in general in the general Lie algebra, general linear algebra. So, okay, so how do I generate my coefficients of the signature? It's enough to apply a Picard iteration to this problem in order to generate all the terms that I have in the signature, okay? So there is a tight connection in between this simple linear problem and the previous more complicated nonlinear problem. What are the interesting properties of the signature? Why do I bother with this signature, okay? Well, the first thing one can notice is that the signature is independent on the parameterization of the path. That's a very desirable property also in data analysis, as we will see afterwards. Another important property, which is very fundamental, is that signature can be given a group-like structure. This comes from a result, it's a famous result by Chen. It's called Chen rules, because this group-like structure corresponds to the product of concatenation of paths, okay? Another thing is that signature are redundant because you can use the rules of integration by parts. This set of numbers here, or sequence of numbers, in fact can be reduced to a simpler sequence. And this can be done by means of, by taking logarithms of formal power series in an appropriate way. And let me go to the connection to Lie group integrators so that these logarithms become a little bit more concrete. And the connection is the following. Suppose now that we're using our Monte-Cos integrator or Magnus, or Monte-Cos formulation of the Lie group integrators. You remember I wrote the solution in this form, and I wrote the differential equation of this sigma curve in the Lie algebra. I assume that I'm solving this ordinary differential equation, linear one here. And I apply Picard iteration now to this new differential equation. Turns out that this is enough in order to generate all the values of the logarithm of the signature. So this is a very nice representation of the signature, non-redundant, and can be obtained by looking at the Magnus expansion for this equation. All right. I promised that I was going to comment on some applications. And just to convince you that this homogeneous space formulation or formulation with Lie group action has some importance. And my favorite manifold in this context are the Stiefel and the Grassmann manifold. In particular, let's concentrate on the Stiefel manifold. The Stiefel manifold is the set of matrices n times p, where n is larger than p, which have orthonormal columns, okay? And these manifolds are very important in a number of applications. Typically, for example, you have problems of reduced basis for model reduction techniques. You have computation of eigenvalues and Lyapunov exponents, and also gradient descent methods for learning techniques, for optimization techniques of various types. Here are a few references of some work that I've been involved with for these different applications. But I would like to highlight this computation of Lyapunov exponents. If you want to study or to analyze stability of nonlinear dynamical systems, then one way to do it is to look at Lyapunov exponents. What are Lyapunov exponents? What you're doing is you're taking your trajectory, your solution x of t, and you linearize your problem along this solution. This gives you a matrix, a fundamental matrix ODE, which is given here. A of t here is simply the Jacobian of the vector field along x of t. And then you can compose you can make a matrix out of another matrix lambda out of u by taking u transpose of t times u of t and taking the limit as t goes to infinity of this power here. Okay? So the Lyapunov exponents are the eigenvalues of this matrix. So, and they are very important because if they are positive, it means that your problem is chaotic. If they are negative, it means that your problem is stable. Problem is that it's not so easy to compute them. It's not so easy to find them. And then there are a number of techniques for computing Lyapunov exponents, and one was proposed by Dieci and Van Vleck. And in particular, they also say, okay, perhaps it's too expensive to compute n Lyapunov exponents for an n-dimensional dynamical system. Perhaps you want to compute just p of them, just a few of them, okay? And what you can do in that case is to consider this ODE on the Stiefel manifold. This is reminiscent to some flows that Brocket has been formulating for computing eigenvalues of matrices. So this is the flow you should compute, and then turns out that you can prove that the Lyapunov exponents are just given by this formula here. So the proposal is approximate this flow on the Stiefel manifold and then compute this approximately. So make a quadrature to compute the approximation of the Lyapunov exponents. And I want to show you an example here. So for example, this is a benchmark problem that has been used in several references in the literature. It's a ring of oscillators, and it's y here is a forcing term, and x are the variables of the oscillators, the position. And we have this nonlinear potential here that is driving the oscillators. And this external force here is switched on only for the first component. So it's a simple problem. So what this shows is that, in fact, the method computes the first 8 Lyapunov exponents in an appropriate way. It's similar to the literature, to results in the literature, and it is quite efficient because you can work just with n by p matrices, and is kind of efficient. In fact, there are a number of details that one should describe in order to convince you that this is really a cheap method, but I don't have the time to do this now. All right, let me proceed. When you are a numerical analyst, you should be concerned with error analysis and not only with the design of methods. And here is a work that we have done recently for extending error analysis for Lie group integrators, in particular methods which are designed on Riemannian manifolds. What do we do? So the setting is as follows. We have a manifold, a Riemannian manifold with a Riemannian distance on it, and we assume we are given a retraction. For example, this could be the composition of the Lie group exponential with the Lie group action. This is what I had in my previous example. Or you could have the Riemannian exponential if you prefer. And what we do in our analysis is to proceed similarly to what you do in a classical context. You have first to make a local error analysis, and then to use these local error estimates to prove convergence. So here is the local error analysis. That is quite simple. That is relatively simple. Because in fact, you can prove that your vector field is pulled back to the tangent space. And your method, you can think of your methods as integrating locally your problem on the tangent space over one step. And then the order analysis is simply reduced to consider local order analysis at this stage. So you can apply the classical theory in the tangent space, locally, okay? And then you get, for the Euler method, you get an estimate of this type. So here note, we compare the numerical solution at time n+1 with the exact flow exiting from the numerical solution at time n. Okay, we make this choice. This is a way of defining the local error. You could do it in a different way, but this is the way we define it here. And then the global error follows, but you need to be a little bit more careful. Well, we assume F is a complete vector field, and we have a connected Riemannian manifold, and we assume to have our local error estimate that I discussed in the previous slide, and then we need the following property. We need a sort of Lipschitz condition on the vector field. And what is that? Well, we express in terms of the metric, the Riemannian metric, this Lipschitz, we want the covariant derivative of the vector field to be bounded by some constant L, which is some sort of Lipschitz condition, okay? And here, this is the Levi-Civita connection. All right, so if this is true, then you can prove your global error bound, which looks like so. And the main idea or the main ingredient of the proof is a Gromval-like inequality, which is due to which we found in this paper, okay? This work. So let me try to explain this this picture here, because I made such an effort to make it. So if the green line here is your numerical method, and the red line is the exact solution, so what you have here, you see at each step, you exit from the numerical solution, and you go along the exact solution. These are red lines, so exact solution, for a little while, and you have this difference here. This is your local error. Here is again your local error, and here is again your local error. But then you have to make sure that this part here, that is accumulated throughout the steps, the error is accumulated. These parts here are accumulated, but they are not exploding. They are kept controlled. And this picture is the analog of what in Euclidean space is called the Lady Windermere fun type of argument that is very classical in numerical integration, and is also used for PDEs, not only for ODEs. Okay, I'd like to ask how much time? Wow. All right. Okay, I think you have to stop me at some point. I wanted to describe a little bit of these methods which combine manifold structure with integral preservation, preservation of first integrals. And this is also a recent work, and this nice plot is due to Sölve Eidnes. So we have been, so energy preserving methods based on discrete gradients for Euclidean spaces are very well known. And they were designed in the 90s at least. So what we have done recently is to extend this to Riemannian manifolds. And what we are doing again is the setting as before, and we have a manifold, Riemannian manifold with a metric, and we have a retraction on this manifold, and we assume that our ODE has a first integral. So we assume that the energy H is constant along the trajectory, okay? So what we want to do is to use the Riemannian gradient to describe our vector fields. So the Riemannian gradient is the unique vector field that satisfies this property here. So it relates the differential of H with, by means of the metric with a vector field, okay? Turns out that under mild assumption, technical assumptions, you can always write your system, your problem, into this form here by means of the gradient vector field and by means of a skew-symmetric tensor field. So it's important that this is a skew-symmetric tensor field. So in the context of Euclidean, in the Euclidean case, this is simply the gradient, the usual gradient, and this is simply a skew-symmetric matrix. So you can do it, and you can easily prove also that if your system is in this form, then you have energy conservation. Okay, what do you do to design a method for this problem, this sort of problems that preserves the energy? Well, the recipe is as follows. You have to discretize the gradient and the skew-symmetric tensor field separately. So you discretize this skew-symmetric tensor field so that it remains skew-symmetric, and you discretize the gradient so that it becomes a discrete gradient. And now I want to tell you what is a discrete gradient. So here is the definition of a discrete gradient. In fact, the definition of a discrete Riemannian gradient. You have two, I'm not going to be very careful here because it takes too much time to say all the details. But there you have two main properties. One property is consistency with the proper gradient. So if you apply, your discrete gradient will depend on 2 points. If you apply the discrete gradient in the 2 points P and P, then you get back your gradient, okay? The second thing is this property here, which is an orthogonality property. So orthogonality-like. If P and Q are on the same level set of your energy function, then this is equal to 0, and this is an orthogonality in terms of the Riemannian metric, okay? So here it's again one of my pictures. This is the level set of the energy. Suppose that the 2 points are on the same level set. Then if you look at this in the tangent space associated to this point C here, I have to find a common tangent space on which to look at my problem from. And then if I look at that, I look at the difference of the two images of P and Q in the tangent space, then the gradient, the discrete gradient, should be orthogonal to this line here. Okay, examples of discrete gradients. This is in the context of there are many examples, but, well, at least 3. And the discrete gradient I'm going to discuss or to use in the experiments is, in fact, a coordinate increment discrete gradient. And it is derivative free. It's nice in problems of image processing. Okay, how do you go about for getting your method? Well, your method is going to be expressed as follows. You have un plus 1 is the retraction applied to a certain vector w, where w is given in this format here. So if Cn here was equal to Yn, this term is going to be 0. And think about that situation. Assume this is 0. And here you see that we have discretized the skew-symmetric tensor field on its own and the gradient with a discrete gradient. And then the proof of energy preservation follows really straightforwardly. It's a 2-line or 1-line proof. Okay, I want to apply. Turns out that these methods, yes, I described them for energy preservation, but they are also automatically dissipative, energy dissipative, if you apply them to gradient systems. Okay? So I'm not going to dwell much further about that, but try to explain a couple of applications of this. And the first one is interferometric synthetic aperture radar image denoising. Okay? So what we are doing here is to apply this problem on manifold value images. And these are produced by this technique, INSAR technique. So what is this INSAR technique? You have an antenna which is sending pulses, is sending radiations to the ground, and and the ground is reflecting back some radiation that you record. And in particular, you record this information in terms of angles. And so what you can do with it is to detect surface deformations on the ground, for example. Or you can, for example, you can study problems of earth science like the profile of volcanoes, and I will have a picture about that. All right, so these are angles that your images are the pixels of your images are angles, so they are elements in S1. We consider this metric distance, Riemannian metric distance, very simple, and one important thing you want to do with these images is to denoise them. And then what we have applied is this total variation denoising technique. So here we have something that we minimize. This part is something that we minimize, and this part is the regularizer of the problem. So S here is your input image, and U is your output image. And here is the result. The top line are the original images, and at the bottom line, I don't know if this is good enough to show that, in fact, you have an improvement. You've been denoising the image. Second application is diffusion tensor imaging, and this has been discussed earlier today in the session on Riemannian metrics and statistical things in the early afternoon. And we applied, this is a similar problem. Again, it's a denoising, total variation denoising problem, and the manifolds are the symmetric matrices, okay? And the results are made, or these experiments were made by Torbjörn Ringholm. Okay, I see that my time seems to be up. And the last application, I'm not going to describe this because it takes too much time, but the last application is an application on shape analysis on Lie groups for virtual character skeletal animation. So we look at animations as curves evolving on a number of copies of SO3, and we think of them as shapes. So we do shape analysis for these animations, and we do it into a Lie group setting, in a Lie group setting. And we have two techniques. One is based on the SRV map, which is a well-known shape analysis technique, but adapted to Lie groups. And the second is instead a technique which is based on the signature. And we do that for recognizing motions, for example. So here is an example that was shown also by Nicolas Tapia in his talk at the GSI conference here this year. And you want to characterize all these motions, which are here, walking animations are in green, yellow are the jump, and run is the red. And by using the SRVT framework, this is what you get. You get very nice clusters. Every animation of the same time is tightly put together with small distances, while the next thing is our method, new method, which is not quite giving the same tight clusters, but it has a big advantage that it doesn't need to compute optimal parameterizations. It doesn't need to apply dynamic programming. So it's much simpler, and it shows some promise. But we're still working on the details, further details, and on the understanding of this method. All right. These are my references, and I thank you very much for your attention.
Thank you.